All right, in this video, we're gonna go through the last few problems in this section. And example 11, it says a point rotates around a circle of radius 3 centered at the origin. Sketch a graph of the y-coordinate of the point as a function of the angle of rotation. Okay, so nothing is different here except one thing. Instead of a unit circle, now we have a circle of radius 3. So that means that our highest point, instead of 1, now is 3. And the lowest point is -3. So otherwise, the circle is the same. Okay, so when we will actually make our scale, so we have pi over 3, 2 pi over 3, pi, and then 4 pi over 3, 5 pi over 3, and 2 pi. That's our full period for the rotation of this point, because it goes around the circle. It makes a full rotation in 2 pi. But instead of on the y-axis, instead of going up to 1, this graph will go up to 3 and down to 3. So the amplitude for this sinusoidal function will be 3. Okay, and how do we know it's a sine function? Because we're plotting the y-coordinate, not the x-coordinates. If they asked us to plot the x-coordinate, then we would have a cosine function instead. Okay, so the sine function starts with 0, 0, and then a pi over 2, which is going to be somewhere here, is going to reach its max at 3. And then it's going to go down and cross the axes at pi, and at 3 pi over 2, it's going to reach its minimum and back up to crossing the axes. Okay, so let's do this graph. And again, just wanted to say here that don't forget to extend it, you know, show a few more. Just continue drawing the graph, showing that it's not just this piece, it actually continues on. Okay, now I want you to try this problem, which says, what is the amplitude of the function f of x equals 7 cosine x, and sketch the graph of this function. And pause here if you have to. And our next example is this. Let's focus on example 12 and 13 right now. Okay, so first example 12, it says a circle with radius 3 feet is mounted with its center 4 feet off the ground. The point closest to the ground is labeled P right here. As shown in the figure, sketch a graph of the height above the ground of the point P as the circle is rotated. then find a function that gives the height in terms of the angle of rotation. So here our ground is our horizontal axis, and so the point will always be above the ground, above the horizontal axis, and it's going to go around the center point, right? Up and down. So my midline of this uh, graph will go through this point, which is 4 feet of the ground. Okay, let me make my my vertical axis here. My vertical axis here. Okay, and this is 4. This is, what did they say, 2 feet of the ground? Oh, sorry, we need to find it, actually. So the center is 4 feet of the ground, but the radius here is 3. So this distance right here is 1. Okay. So here's 1. And this means that this highest point is 7. Right? So our point is going to go, this is the lowest 1 and the highest is 7. All right. So and we're going to start with our point downwards in the position closest to the ground, right? 1 foot above the ground. And we're going to call it 0 rotation. At this point, there was no rotation yet, and that will be 0. Okay, and then we're going to have pivot 2, pi, and then 3 pi over 2, and the full rotation 2 pi. So at when the angle rotates pi over 2 a quarter circle, it's going to hit the horizontal line. So it's going to cross the middle line, and then it's going to continue to go up until the rotation is equals to pi. So at pi, it hits the highest point, and then it continues. At 3 pi over 2 is going to be at the middle line, and then it goes down, and for the full circle, now the full circle is completed. Okay, so this is what our graph looks like, actually. Oh, I'm sorry. So for 2 pi, it's going to be down here, but closest to the ground again. Okay, so here we go. This is our full circle. And of course, like if we go for the second, if it continues to rotate, it's going to do this again, same shape. Okay, so we need to write an equation that models this function, and we can actually choose whether to use a sine or a cosine function. And sine function starts with actually at the midline, right? At the and the cosine function has a maximum point at 0. Our function actually has a minimum point, so I prefer to use the cosine with a negative sign, because the negative sign flips the cosine, and it will have the minimum point here. Okay, but let's determine all the other parameters. We need to figure out A, the amplitude, the B, the C, and the D for our function. So I'm looking at the cosine now, and the amplitude is 3. So it's from the center, it's going to go 3 units up and 3 units down. Okay, so what is B? Is there any stretch or compression horizontally? And the answer is no, because I mean it makes the full rotation in the regular interval in 2 pi. So rotation is, I mean, B is 1. There is no stretch or compression. C, what about the shift? Well, I would say there is no shift. It's just the cosine function upside down, right? So if we were to actually rotate it about the midline, this is what we get, and that's our perfect cosine function. So no, there is no phase shift. But if I use the sine function, I would have to use a phase shift of I think it would be a sine function shifted pi over 2 to the right. So C would be pi over 2. But anyway, let's continue. D is the up and down shift, and it went up 4 units. So D is 4. And the amplitude is 3, but because the function is actually flipped, so the A would be a -3. So I'm ready to write my equation. It's -3 cosine. B is 1, C is 0, so it's just going to be x plus 4. That's my equation. All right, let's take a look at the next example. It's actually quite similar, but it different at the same time. It says the London Eye is a huge Ferris wheel with a diameter of 135 meters. That's 443 feet. It completes one rotation every 30 minutes. Riders board from a platform 2 meters above the ground. Express a rider's height above ground as a function of time in minutes. All right, so let's draw this picture. We have a huge Ferris wheel. Here's the center of it, and okay, so it says that the diameter of it is 135 meters. So what is the radius? Radius is a half of the diameter, right? And it's going to be 67.5 meters. Okay, so 67.5 meters. Here, this distance, there is a platform for people to board the ride, the Ferris wheel. So the platform is 2 meters. Okay, and I do agree that my my drawing is not up to scale. This is a high 2 meters compared to the radius, so it's not up to scale. Let's actually make it, when we make a drawing, make it a little shorter like this. So my ground is going to be right here. Okay, my center center line is right here. Okay. So my center is 2 meters plus, so this is 2 plus 67.5. So this is going to be 69.5 meters. And my highest point, 69 plus 0.5 plus 2. So this is going to be 135, 37, 137 meters right here. Okay, now the full revolution happens in 30 minutes, and I want to basically break it down into 4 equal intervals. So I'm going to have 15 minutes in the middle, and then 7.5 minutes in the middle between 0 and 15, and 22.5 here. Okay. Actually, my middle line is a little crooked. Okay. There. Okay. So when people board at 0 minutes, the point is at the lowest. Now, 7.5 minutes later, they completed a quarter of revolution and they came up to the midline right here. Okay, and then 7.5 minutes later, from this point, they are on the top. So right here. And then 7.5 minutes more, they're back to the middle line, and then they're down here again. And the revolution is complete. The full rotation is done. Okay, so a function is going to look something like this. Again, my drawing is not perfect, but anyway, something like this. And again, we're asked to model this function, and I'm again going to use the cosine function. I'm going to identify the A. The amplitude is 67.5. So it goes 67.5 down and 67.5 up. I'm gonna use negative just because I'm gonna use this cosine function right here, and I'm gonna flip it over. All right, so this cosine function has amplitude of 67.5, but it's flipped, so it's negative. What about the stretch, the B? Okay, the period. Okay, so we know the B influenced the period, right? And what we know, where should I write? Okay, I'm gonna write here. What we know is that the period is actually 2 pi divided by B. Our full period for this function is 30 minutes, right? So it's 2 pi over B. And from this, we can find B. Multiplying both sides by B, we get 30B equals 2 pi. So B is 2 pi divided by 30, or pi divided by 15. So from this, we know that B is pi over 15. So right here, I have my two of my parameters that I will be plugging in. Okay, so what about C? What about the phase shift? There is no shift actually, there is a flip. So, yeah, I'm just gonna leave a C equals 0. All right, and what is D? Well, D is actually the distance of the midline above the ground. So D is 69.5 meters. Okay, so I have my other two parameters, and I'm ready to write this function. And this is function of Tx represents time. Okay, so we have negative 67.5 cosine B is pi over 15 times t. C is 0 plus 69.5. All right, so this is the function that will model our the height above the ground. And now I would like you to try this problem by yourself. It says a weight is attached to a spring that is then hung from a board as shown. As the spring oscillates up and down, the position y of the weight relative to the board ranges from -1 inch at time x equals 0 to -7 inches at time equals x equals pi. Below the board, yeah, assume the position of y is given as a sinusoidal function of x. Stretch a graph of the function and then sketch a graph of the function and then find a cosine function that gives the position y in terms of x. And notice that they already told you that it's going to be a cosine function. All right. So pause here and work this problem out. And I'll see you in the next video.